All right, Sarah, I want to make sure to respect your time. So we're going to go ahead and get started here. This is, of course, recorded so anybody else can watch it later. I just have a bunch of problems to go through today, largely related to what I know your quiz is going to be on. But I want to make sure to kind of say this to everybody who watches this. I'll remind people about this in class on Wednesday. There's been a lot of requests. Can we make sure to do problems just like we're going to have on the quiz, just like we're going to have on the quiz? And absolutely happy to do that. But I want to make sure to remind people that we do have an exam on Monday, which has more than just that little nuanced skill of the kind of problem that we're going to see on the quiz. Usually I pick the most important thing as kind of a critical element that I want to make sure people master. But there's other things that are going to be part of what we'll see on the exam. So just to make sure to highlight and show people here, if I go to our Blackboard page and go under exam preparation, I want to just make sure to highlight so everybody knows where this stuff is. There's a study guide for exam 3, and I'm going to be using this on Friday as we kind of go through some problems. But kind of highlighting, for example, in our unit on kinetics here, that was unit 5, we can see that, yes, integrated rate law was a very important skill, but we also have, and you're likely to see problems on your test related to reaction rates and writing and using rate expressions. And then rate law, reaction order, rate constants, you're likely to see a method of initial rates problem. And so we'll make sure to practice those as well. And then again, as we're in unit 6 here on equilibria, a lot of these things sort of build in together. But we are going to spend some time on Wednesday talking about shifting equilibria, so that's going to become a part of it. But the critical skill for Unit 6 really is how do we solve equilibrium problems? And we've been focused on like this type 2 problem where we're using simplifying assumptions, which again, that's what's going to be on your quiz. But we want to make sure we don't forget about doing those other kinds of problems. So I wanted to highlight that just for a minute before we started going through some problems. And so I'm going to run this session just like we've done in the past. Sarah S., I know you're with me every week, so you kind of know how these work. Sarah H., I think you've been with us a couple of times, but just to highlight, what I'm going to do is I'll show you a problem. I'll have the answers listed there so that you can see what the numerical answer to the problem is. And then what I'll ask that you do is in the chat, indicate when you're either done, that you've got that correct answer, or that you're ready, that you've sort of been working long enough, you're stuck, you kind of are ready to work through the solution. And then I'll know we're ready to kind of move on. So here is the first problem. Okay, so hydrogen sulfide decomposes according to the following reaction. We have a Kc value given as 9.3 times 10 to the minus 8th. Remember, I highlighted this in class and just kind of pointing it out right now. When we have temperature values that are given, that's never anything that's going to become part of our problem. It's really just indicating that equilibrium constants, just as rate constants, have a temperature dependence. We'll investigate that more next semester, but this is not anything that becomes part of any of your calculations. A balanced chemical equation is given, as will be the case for your in-class quiz that you'll have on Wednesday. I'm sorry, Friday, not Wednesday, on Friday. And then they tell us that we've got 0.45 moles of H2S placed in a 3-liter container, and we want to know what's the equilibrium concentration of H2, again, at that same temperature. That's the only reason that that's listed, is we need to make sure we highlight that those, that we're not changing temperature, because that would sort of change the system that we're in. So here's the answer you should be getting. I'm going to let you ladies work for a little bit. Use the chat, please, to let me know when you're, again, either done, you got the right answer, or ready, you feel like you've wrestled with it long enough and you're ready to see a work through solution. I'll be here if you have questions. You can feel free to unmute, put something in the chat. If I don't see something in the chat, there's not a bell or something that goes off to let me know. So just unmute yourself and just say that you have a question in the chat. But I'm going to let you guys work and we'll revisit in a little bit. All right. So let's take a look at this. So we have one done, one ready. So I will make sure to go through this slowly enough. And I have the solution all on kind of the next slide. So it's all kind of there all at once, but I'll take it a piece at a time. So, and then Sarah S., I will sort of pause at each point and I'll see if there's something I can address. And I will ask you, if you don't mind, we can share maybe where you got stuck, because it's always helpful when other students hear where people can get stuck in these questions. Okay. And just like we did in class, I have these pieces kind of numbered how we did them before. And so the numbers might be a little bit different here. I might correct them here as we go along, but let's just kind of highlight what we have here. First step is always writing and using our balanced chemical equation. I told you guys that's going to be given for you. Second step is writing your equilibrium expression. And so we've got that there. A couple of things to note when we look at this, as we start looking at doing different kinds of problems, we're going to note that when we have a small equilibrium constant, that's going to be a good indication that we probably will be able to successfully do an assumption. Remember, an assumption is if I've got a pile of reactant and I'm trying to figure out how much product I make, if I have a small equilibrium constant, that means I'm not making a lot of product. So that scoop that I'm going to take out of my reactant pile to convert to product is going to be really small. That's what this guy is. That's the scoop of reactant that goes and becomes product. So when I have a small equilibrium constant, I know that scoop is going to be small. So that's a good indication that I probably can safely make an assumption. Okay. Third step is making sure that things are in the right units. So this can be a place where students can make a mistake, because if you try to do these calculations using 0.5 there, you're not going to get the right answer, because we need to have molarity or atmosphere in our ice tables, depending on whether we have Kc or Kp respectively. So in this case, we need to convert our starting concentration for our H2S into molarity. So that's 0.15 molar. Next thing we need to do is fill out our ice table. So that's what we have here in the middle. Okay. We know that since we have none of the products that we formed, that our reaction is going to shift to the right. Okay. So that means we're going to lose 2x of H2S, gain 2x of H2, and gain x of S2. As we propagate that down to our equilibrium row, we're going to have 0.15 minus 2x, 2x, and x. And I'm going to pause there for a second. And Sarah S., see if you have any comments or questions at this point.
No, I'm with you there. I already see where I went wrong.
Oh, okay. I'll ask you to share that in just a second. I'm going to pause here for a second because my children are watching television and it's loud for me. So I don't know if it's loud for you guys. So hang on one second. Okay. So then the next step is we need to solve for x. So the fifth step was solving for x. And so that's where we take our equilibrium constant and our equilibrium expression, and we put these pieces into that equilibrium expression and we solve for x. Now, algebraically, this is going to be a fairly complicated problem if we were to have not only x cubed terms, but x squared terms, x terms, and constants. Actually, there's not a way to solve that problem, with any math that I would expect you guys to know. So an assumption is going to be important because it's going to allow us to simplify this 0.15 minus 2x to 0.15. Now, maybe, Sarah, this is where things happen. I'm going to ask you in a second. It's not uncommon for students to miss that square that's there, so they forget that square that's there. Or sometimes when they're combining these terms, they may get something incorrect there. Okay, and then once we have this and equal to our Kc value, then we're going to solve for x and get x as here without rounding yet 8.057 times 10 to the minus fourth. So Sarah, did we get to a point yet where you had made a mistake?
You nailed it. I forgot the squared
In that
with the 0.15.
Yep. That and again, this is one of those things where good news on the exam, there'll be an opportunity for partial credit. On the quiz, it has to be something that we get all of these pieces right, because you can kind of know what you're doing, but forgetting a small piece like that could be a way to have a mistake. Okay, so fifth step is solving for x. Step 6 is going back in and solving for what your equilibrium quantities or whatever the problem is asking. In this case, it's asking about the equilibrium concentration of H2. I actually put all of them in here because this problem could just be reworded and made to be a different problem by just saying what's the equilibrium concentration of any of these things. So, and these, I did not round these to the right number of significant figures here. I just sort of kept them. So we would round everything based on what we see here to 2 significant figures. So this would be 0.15 molar for H2S, which is essentially the same as what we started with. But then we've got small amounts of the H2 and S2 gas that we would make. So it's going to be double of what our X value is. So it's 1.6 times 10 to the minus third. It would be 8.1 times 10 to the minus fourth for our S2. Couple of things to highlight. You won't need to do this for your quiz on Friday, but it will be part of what you need to do on an exam question to get full credit for a question that you need to make an assumption for. And this is what this step 7 is. You have to prove to me that doing that assumption was valid. So we can do what's called the 5% check. That's the 5% rule. I'm going to talk about something else on Wednesday, which I know I talked about in the video, which is a 400 rule. So there's the 5% or the 400 rule. So what we basically need to do is take X over our starting amount. And, you know, in reality, we probably should put in, and it's not going to matter too much mathematically here, but this probably should be 2X. Because we're saying the size of our scoop is a 2X, and we're making the assumption that that 2X is small. So we can see here that would still be 1%. So that's not going to change our value here. But if it was something that was on the border, that would matter. But in this case, we take the size of our scoop, divided by the size of our pile, multiply by 100, and that tells us that the size of our scoop only represents 0.5%, or in reality, 1%. Of our total amount of starting material. So our assumption was valid. Okay. This is not a step that's required, but I wanted to kind of highlight to you guys a great way. And I encourage you to please do this on your test or on your quiz for Friday. Take a couple of minutes and then put your values back in to do a check. Now you're only going to be asked for one equilibrium value on the test in order, or on the quiz, to enter in for that Blackboard value. But I encourage you, figure out what all the pieces are, because then you can take those pieces, and what you're really doing is putting those pieces back into this equilibrium expression, which is what I have shown up here. And then you should get back your equilibrium constant. And remember, it's not going to be exact because we made an assumption. We sort of ignored the size of a scoop here to kind of get an answer. So it's not going to be perfect, but it will be within error of what that value is. So on Blackboard, when you submit answers for this, you will actually get, and this is part of the reason why I do 5% anyways on previous quiz questions. That accounts for the fact that you might be off by 5%, and we're going to assume that that's negligible. Okay, but please, 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 before you submit your answer, do this little check. If you can put the values back in that you had, and you can get your equilibrium constant, you can have more confidence that the answer that you got is correct. Okay, so I'm going to pause there for a second, see if either of you have any questions on this guy.
Hey, not on the problem itself, but this is the first time I'm trying to do a cube root on my calculator. I'm still trying to figure it out. I know how to take the square root. I haven't figured out how to do a cube root on my calculator.
Which calculator do you have? If you
It's
want,
the one you recommended at the beginning of the course.
Let me grab mine, and that way I can show you. I got to find it on here. Gosh, I hate getting old. My eyes are getting old where I have a hard time seeing it. Okay. So there's this button here. That's the caret symbol. That's the symbol, the naughty symbol that a lot of people use when they try to do scientific notation. Just another little reminder, especially if you have this calculator that I have that I recommended. There's over, it's a little bit dark here to see. But over the X to -1, that's where the EE button is. Make sure that you're using that button if you're doing scientific notation. Don't use the caret symbol and say, 10 to the whatever. It's just a way to sort of get in trouble when we're doing scientific notation. But we are going to use that symbol right now. Okay. Now, this is what you're going to use if you're going to put something to kind of a power. You're going to put something to, like, you can put it to the 4th or the 5th power if you had something that wasn't your typical square. And above it, you can see that it looks like a square root symbol with an X that's in there. Okay. So for example, and I just want to make sure, let's see, 20. I want to see how to put this in here. So 20, I'm trying to take the cube root of 27 because I know the answer should be 3. So let's do cube root 27. 3 in first.
Okay, I typed in 3 second and that button, caret button, and then I hit enter and I got 3. Is that correct?
So let's see. 3. Good question. So here's what I like to do. Look at this. If I do this, let me make sure that this works. And then I'll show you. Yeah. Okay. This is actually how I like to do cube roots. Let me make sure that I can see this here. Oh, that got away. 97 to the. Okay. I like to put it in like this. And I've got reflection here, so I'm trying to get it where you could see it. It says 27 caret. The cube root of something is taking it to the 1/3 power. Does that make sense?
Yes, it does.
I think that's the easiest way to do it. I know there's that button there, but I can't figure out how to use that button. And I don't want to get lost in calculator functions here when I know this way works. So if you need to take the cube root, it's to something to the 1/3 power. If you need
all right, that works.
If you need to take like to the, if you're not cubing it, it's like to the cube root power or to the 4th root power, it's times 1 to the 4th. I don't think we're ever going to see that. Cube root is definitely a possibility. But yeah, if I do this and then I press enter, just to show everybody who's watching, that gives me the answer 3, which I know the cube root of 27 is 3.
All right, thank you.
Yep. Anything else from either Sarah? All right, here's another problem for you to work on. So even at high temperature, the formation of NO is not favored. This is again another way of highlighting, you might see a part 1 question where I might give you an equilibrium constant and I might ask the question, which is favored the formation of reactants or products? When you have a small equilibrium constant, we're not forming or favoring the formation of products. So we're given the balanced chemical equation for that. We're given the Kc value for that. It's a small Kc value. And again, that temperature value, not anything we need to do anything in the calculations for. It's just indicating, hey, when we're doing this or considering this reaction, we need to keep the temperature constant. Otherwise, we're going to affect things. And we're going to talk about that a little bit more on Wednesday. So this is asking us, what's the concentration of NO when a starting mixture of 0.2 moles N2 and 0.15 moles of O2 reach equilibrium in a 1 liter container? So the answer is given there in blue. So let me know when you either have gotten the right answer or you're ready to work through the solution. And again, Sarah S., I know we know what the answer is here, but you probably weren't quite certain as you went through that last problem where you made a mistake because you knew you didn't get the right answer. But I'm just highlighting this again for everybody, on Friday's quiz, do that check at the end to kind of make sure that the answer that you get fits into what you'd expect to do when you put those numbers back into your equilibrium expression. You both seem to put your responses in at the same time. So we still have a done and a ready. So this time Sarah S is done and Sarah H is ready. So let's go through this solution. Okay, so again, I'll go through it slowly, and Sarah H, I'll probably ask you this time, maybe where you got stuck. So again, everything is kind of thrown out here all at once. So we'll go through it little piece at a time, kind of using the number system to kind of walk through the pieces that we have. Balanced chemical equation is what we need to start with. Then we're going to write an equilibrium expression. And these are all type 2 problems that we're doing today, which means they're giving us an equilibrium constant, which we're going to use to solve for equilibrium concentrations. And so here's our equilibrium expression. It's equal to this equilibrium constant. Third step is always making sure that things are in the right units. With a Kc value, it needs to be in molarity. And so they gave us moles, but since it's in a 1 liter container, you actually would get the right answers if you just put in 0.2 here, because 0.2 mole in 1 liter is 0.2 molar. So initially, we set up our ice table here. So initially we have 0.2 molar N2, 0.15 molar O2. And we know we're going to lose a little bit of that to make some NO because we have none of that to start with. Okay, so propagating our ice table, we get our equilibrium values as 0.2 minus X, 0.15 minus X, and then 2X for the NO concentration. Then to solve for X, we take these pieces and we put them into our equilibrium expression. So it's going to be 2X the quantity squared in our numerator, 0.2 minus X and 0.15 minus X in our denominator. To solve this without having to use the quadratic equation, we make an assumption that X is small. If X is small, then our denominator simplifies to be the product of 0.2 and 0.15. That equals our Kc value. Going through and solving for X, we're going to get X equal to 1.75 times 10 to the minus third. So I'm going to pause there for a second and see if either of you have any questions. And Sarah H, I might ask you, did you get up to this point or did you get stuck someplace? And it's probably not that you got stuck. It might just be a math mistake maybe somewhere. And you can feel free. If you were saying something, I couldn't hear you, you were still muted, you could put something in the chat. I always think it's helpful to kind of hear maybe where people got stuck. All right, just think, and that, you know what, that's a common thing. People can just type things wrong into their calculators. So had everything wrong or everything right up to this point. So once we've solved for X, that's our 5th step. Our 6th step is to answer the questions by putting those equilibrium or figuring out what those equilibrium values are. So our NO concentration is going to be equal to 2X. So that's going to be 3.51 times 10 to the minus third. Our N2 and O2 concentrations are going to be 0.198 and 0.148 respectively. Now, to keep with significant figures, I probably should round all of these to 2 significant figures, but I'll even give myself plus or minus 1 significant figure. So this would be 3.5, this would be 0.20, this would be 0.15. So again, the issue with having those is then it doesn't look like anything really changed. You know, obviously we're going to be making some of this, but I do think I sometimes keep these with 3 significant digits. So we do recognize that we do lose a little bit of our starting material, but in terms of significant figures, if we rounded that, it wouldn't appear that we made any change. So not important for your quiz on Friday, but important for the test on Monday. If you do make an assumption, you need to go through and do that required check to show me that your assumption was valid. So in this case, we're going to take the X, the size of our little scoop, and we're going to put it over one of our starting values here. Actually, I'm going to put it over. There's 2 options here. I always chose to take choose to take and put it over my smallest starting material because we made an assumption for both of these. We made an assumption that the X was small when subtracting it from 0.2 and that the X is small when subtracting it from 0.15. This is going to be the one that's potentially more problematic because it's a smaller starting pile. Okay, so that's why I use the 0.15 here, but we can see that we are less than 5%. So we're okay with that. Again, this is highlighting the optional piece. If you want to do that check, put your values back into your equilibrium expression. Okay, so I'm going to put my concentration of NO in there and I'm going to square it. So that's this piece here. Let me zoom this in because this is really probably tiny for you guys. Put my NO concentration in and square it. And then it's the product of those other two. And I should get something that is within error. And we can see it's within error of what my starting concentration or my starting equilibrium constant was. So that's just a nice way as a check to make sure that, hey, this answer is probably going to be okay. Okay. So let me pause there for a minute because that was kind of a quick run through of this problem. So Sarah S., I think you got that problem.
Yep.
Awesome. Okay. And then Sarah H., sometimes you're right. It just is something like I typed something wrong into my calculator and so forth. So, or maybe, you know, at some point you realize, you know, that, oh, I missed a square or something like there. So hopefully you're good. But if you're both are good, we'll move on to the next problem. All right. Here's another problem. Dinitrogen or nitrogen dioxide decomposes according to the reaction given there. Kp is given as a very small number, 4.48 times 10 to the minus 13th at a certain temperature. So now we've got 0.75 atmosphere of NO2. We're adding that to a container, allowing it to come to equilibrium, and want to know what the equilibrium partial pressures are of NO and O2. Just making sure to highlight, we did spend a couple of days talking about gases, but we really didn't do, you know, what we typically have done when we do deal with gases in Gen Chem 1, which was actually, it's an entire learning unit, and we kind of have 3 days on it. So I really did it only in 1 day, but just highlighting when we see these terms that say equilibrium partial pressures, that's really saying what are the equilibrium concentrations of these two species. Partial pressure represents the individual concentration as we measure gases by their pressure. Okay, so the language might seem a little bit weird there, but that's a good refresher with what we think about with gases. Let me just take a second and write this down. So equilibrium, this partial pressure really represents the concentration of the gas as it contributes to the total pressure. So we've seen this before. This is going to be an important kind of equation to think about. We've got the total pressure is equal to the partial pressure of some gas A and the partial pressure of some gas B times the partial or plus the partial pressure. So that these all sum up so that each gas contributes to the total pressure. So it is important to kind of review or revisit that a little bit, because if we are going to be talking about Kp values, that means we're measuring amounts of gases in terms of partial pressures measured in atmosphere. So it is important to remember that in this case, you know, the total pressure would be the sum of all of these, but this problem is asking us not what the total pressure is. It's asking what the individual partial pressures are, which is just basically the concentration of each gas as we finish that problem. Okay, so I'm gonna let you guys work on that. Let me know in the chat when you are done versus ready for this problem. Yay, we have 2 dones. That's awesome. Okay, so what I'm going to go through right now is less for benefit of the 2 of you, since we got the right answers, as to anybody else who maybe was just looking to see the worked through solution here. So again, pieces that we have here, there's a lot that's kind of written down here. So kind of highlighting some things that I already said in words. KP is very small. So when we see these small equilibrium, yeah, she needs to go out. You can let her out. She was just outside. I brought her in because she was barking at somebody walking. So small numbers are going to be really good when we want to do assumptions. Okay. So first step, write your balanced chemical equation. It's already provided for us, but I use it I have to rewrite it anyways to kind of have my ICE table. We're doing a KP value. So the only difference in how we formally sort of write our equilibrium expressions is we're going to have not brackets for concentrations. We're going to have parentheses to indicate partial pressures, but everything else is going to be the same. We're going to have coefficients become exponents here. When we think about units that we have for things here, they're going to be units of atmosphere. So when we have these units, it tends not to be something that we have to do any additional sort of manipulation with, like we did on our last problem, where we sort of needed to calculate molarity because we were given moles and then the volume of a container. Going through and doing our ICE table here. We know that we have none of the products that are made, so that's a clear indication that our equation is shifting in that direction. I will highlight for your quiz, you're not going to have to see a problem where you sort of have to sort out which way do I shift, but it could be something come test time that you may have to do a little bit of a Q versus K comparison to figure out which way the equilibrium is going to shift. Or again, that just might be part of the initial part of the problem, is just saying which way will this equilibrium shift? Will you make more reactants, or will you go ahead and, or will you make more products, or do you have to go and make more reactants? Propagating our change column, pretty straightforward, just like we've seen before, using coefficients to go in front of those X terms. And then we get our equilibrium expression, or equilibrium concentrations expressed in terms of X. Take these pieces, we're going to put them into our equilibrium expression. And in this case, our algebra becomes simple if we can say 0.75 minus 2x is equal to 0.75. So Sarah asked, glad to see you remember that squared term needs to stay with the 0.75, even though we get rid of that x term. And so going through and solving for x, we're going to have another situation where we have to take the cube root of something. So I was glad, Sarah, that you asked for that, so we can make sure to highlight for anybody who needs to do that in their calculator that they know how to take a cube root. Once we solve step 5, which is solving for x, we need to take this x and put it back in for these terms in order to get what these values are. Remembering that the units for these are going to be atmosphere. That's going to be not relevant for your quiz on Friday because it's just a numerical answer that you need to put in. So in this case, the partial pressure of NO2 is going to be 0.75. This is such a small value, such a small, tiny little scoop. It essentially looks as though we didn't take any away. So in that case, that one is going to just look like there was no change. But we do make very small amounts of these other 2 gases. So again, here's our little checkup on top. If I wanted to take these answers and put them back into my equilibrium expression, I should be able to get back to a close representation, at least within the ballpark in terms of whatever the exponent is here of what my equilibrium constant was. Remember, we're making an assumption. This assumption is actually even pretty good, pretty valid. It's well within the 5% rule. Again, not relevant for your quiz on Friday, but relevant for the test on Monday. If you do make an assumption, I need to see that you've checked your assumption and that it's okay. And again, I don't want to muddy the waters here. I'm going to talk about this on Friday or on Wednesday when we go over the answer to the problem that we finished class with today, that some people were kind of getting towards the answer, but if you didn't get towards the answer, I want you to work through it before Wednesday. The 5% rule is something that it's a check that you do all the way at the end. I'm going to teach you guys a strategy that you can sort of do a pre-check rather than this post-check to tell whether or not it's something that you're going to be able to do your assumption with. So I'm going to pause there for a second. I know you guys had the right answer, but just to see if there's anything I can clarify or if you have any questions.
Nope, I'm good.
All right, where are you guys at? I do have a couple more problems that I could work through if you wanted to work through some problems, but I think we've had a couple of problems here that you guys have gotten correct. So I'm happy to stick around. I probably will. Oh, the fire alarm is going off in your residence hall. All right, so Sarah had to take off, which is not a problem. Sarah S, it's up to you. If you wanted to stick around, you know, I have, I think 2 more problems to go through. I think there's 2 more problems I had to go through. So if you wanted to try another one, or if you're like, you know what, I'm pretty good, I think I got this. It's up to you.
These, I mean, the ones we've done are pretty representative of what they're all going to look like. Okay, so I think for me, I just need to make sure I don't forget like those little exponents.
Yes.
So I do have a biostatistics exam that I have to study for. So.
Okay. Yep. You go ahead. What I'm probably going to do here is I am going to wrap up this video a little bit more quickly then, because I will go through these next 2 problems, but I don't have to wait for students to work through them just because most of the students who watch the video can just pause the video and work on it on their own. So good luck on your biostats tests. And then if you wanted to check out some additional problems later on, you can kind of come and do that.
Thank you so much.
You're welcome. We'll see ya.
Bye.
Bye. All right, so I have a couple more problems I will work through here. I will kind of flip to the screen where if you'd like to pause and just kind of wait and try to work through it on your own, you can just replay the video or, you know, unpause the video when you're ready to kind of work through the solution. Okay, so I need to tell my children to be quiet here because they're playing video games upstairs and they're quite loud. So one moment, please. All right. So here's a problem. If you want to pause the video so that you can take a minute to write down the prompt, the answer is written there. I'm not going to wait too much time before I kind of walk through the solution here. Oh, and thank you, whoever took care of that. Was our cat or our pet drinking fountain that apparently is out of water, so it's starting to make noise. All right, so pause this if you want to kind of look through this solution. This is a generic problem, so this is something that there will be some problems that I will make available online that you kind of go through, multiple choice problems that you can practice. They're all based on different variations of this sort of generic equation. So the nice thing with a generic equation is it's just easy to make different permutations of them. So for this one, it tells you that the initial concentrations of A and B are these values that are given here. Everything else is 0. Equilibrium constant is given as 3.9 times 10 to the minus 6th. If you didn't know, remember when you see E minus 0.6, that means times 10 to the minus 6th. This problem is asking, what is the concentration of C at equilibrium? Okay, here's the value. So go ahead and try this problem on your own if you'd like. And then when you're ready, either keep letting it play if you just want to see the solution, or pause and then work on it and then let it play again to see the solution. All right, so here's the solution for this one. Again, I don't have these labeled, but let's go ahead. We can actually label these right now. Make sure you've got a balanced chemical equation. Okay, so that's given for us. There's not really a way to balance it, so we have to make the assumption that the equation is balanced and provided for us. Okay, second step is writing an equilibrium expression. One of the things that's unique to this problem is noticing that D is not part of our equilibrium expression, okay, because it's a solid, so that's not relevant here. Third step is making sure that everything is in the right units, okay? It didn't tell us that we had a KC, but we can see that we've got things that are N molar, so we do know that we have things that are in the right units. So everything from steps 1 through 3 is kind of set up easily for us. Fourth step is doing our ICE table. So pretty straightforward here. We've got some unique coefficients that we have here, which are going to relate to some unique powers that we might see here with our stuff. And so we're going to have our initial concentrations that were put in. We have nothing on the product side, so we know which direction our equilibrium is going to shift. We're going to be making more product. So minus 2x, minus 3x, plus 2x. So we've got those unique coefficients that we have there. And then our equilibrium values are given as 0.15 minus 2x, 0.25 minus 3x, and then 2x. So putting these in here, now we're going to have kind of some unique things to think about, because we've got squared terms in our numerator, square and cube terms in our denominator. But we make this algebra simple by doing an assumption. So that assumption is going to let our denominator simplify to 0.5 squared and then 0.25 cubed. So as we talked about earlier when we did some of these problems, really important to make sure that we don't lose, even though we've made an assumption, we still have to have that cube and that squared be part of those problems there. So that's going to be equal to our equilibrium constant. Going through and solving algebraically for x is equal to 1.85 times 10 to the minus fifth. Putting that x back in this case, the problem is only asking for the concentration of C. So C is going to be twice times whatever x is. So that's how we get the 3.7 times 10 to the minus fifth molar. Now we always need to make sure that we do a check here. So the check is going to be taking that x value. And in reality, we probably should take this 2x or even this 3x value, because we're making the assumption that even double or triple what that x value is small enough to ignore. But because this is the value that goes with the smaller kind of size of our starting pile, you could do that 2x. So in reality, we probably should have twice that up there, but such a small percent here, that 0.02 is certainly much less than our 5%. So we're within the margin of error of being able to do that assumption. Okay, so that's another kind of example problem. All of the problems we've seen prior to this have been actual chemical formulas. So I wanted you guys to get used to seeing one that was generic. Again, what I love about the generic ones is it's super easy to make a different version of the problem by literally just changing these coefficients. Because it's fictitious kind of species here, I don't have to worry that changing a coefficient now throws the chemical equation out of balance. So it's a nice way for me to create new problems without having to create new chemistry. Okay, so that's another one of those problems. I think there's one more here. So this one talks about, this one actually is going to start getting a little bit dicier, because we've got Kc values that aren't so small. So I'm actually going to stop the video here. These are going to be problems that maybe we'll address a little bit more on Wednesday or even in Friday's class, or even in our review session, because these are ones that are more likely to be things that you may see on your exam. But even at that, if they're ones that involve the quadratic equation, which will highlight this problem, and then there was one problem after that that might, they're actually going to be not ones that you're going to see on your quiz or on your exam, but still an important skill to be able to recognize why those problems don't work. So I'm going to wrap it up a little early tonight, just because I don't have anybody else here who needs any questions to be answered. So good luck, and we will see you in class.